In the last few videos, we talked about limits, and I mentioned the limit of a function as x approaches to a number does not necessarily equal to the limit value at x equals to a. In this video, we will talk about what do we have when limit of a function equals to the function value. That is continuity. A function is continuous at x equals to a if the limit as x approaches to a equals to the function value at a, f of a. That is, we have two conditions. The first condition is, well, my limit has to exist. And from the last few videos, you know that the limit exists means that my left-hand side limit equals to my right-hand side limit equals to a specific value, let's say L, and L must be a real number. Now we have an extra condition, that is the limit has to equal to the function value as well. So this L, or the limit of the function, needs to equal to f of a. In other words, if we only have this condition, the limit exists, but it's not continuous. If we have both conditions, then it's continuous. That is, now you have three things to check. You need to check they are equal to each other, and, well, all three of them need to equal to each other. If a function is not continuous at a certain point, then we call it discontinuous, and there are several types of discontinuity. In most of the courses, we only talk about the following three types. The first one is called removable discontinuity. The second type is called jump discontinuity. And the third type is called infinite discontinuity. The first type, removable discontinuity, is when you have a hole here. This hole, we can define this value at somewhere else, or we don't even have to define this value, but when x approaches to a, you can see that the limit exists. If you approach it from the left-hand side or right-hand side, you're approaching the same value. So limit does exist, but it does not equal to the function value. So algebraically, this is what we have. That is, if we're not given a graph, you only have the expression of the function, you can compute the limit, check if the limit exists, and check if it equals to the function value itself. If they don't equal to each other, then you have a removable discontinuity. Next, you can see this graph, we go from here and then stopped because, well, there is a hole here, and then to continue with the next piece, you need to take a jump, and that is why we call it jump discontinuity. Graphically, it should be obvious why we call it the jump discontinuity, but algebraically, what does it mean is basically the two-sided limit do not equal to each other. You can see that this one and this one, there is a big gap in between that you need to take the jump to the next piece. So algebraically, this is when your limit from the left equals to a number, let's say L, for example, but your limit from the right equals to R, and they don't equal to each other. And L, R must be real numbers. They cannot be infinity or negative infinity. The last one we will talk about here is called infinite discontinuity. This is quite self-explanatory because, well, this is when your limit goes to infinity or at negative infinity. So I'll just add a graph here. You can go to negative infinity as well. So algebraically, that's what it means. Or you can call it, well, whenever you have vertical asymptote. Plus or minus, doesn't matter. So I'm gonna write it like this. Plus or minus f of x equals to plus or minus infinity. This is when you have vertical asymptote. Vertical asymptote. This is a, and this is function of f of x. I mentioned that in most of the courses, those three are the ones you talked about because, well, there is actually one more, but most of the places don't really talk about it. Let's look at the graph of this function, sine of 1 over x. You can see that this graph oscillating whenever you get close to 0. So this type of discontinuity is called oscillating discontinuity. And it happens when you have something like sine 1 over x, cosine 1 over x, etc.